Hello friends, I welcome you in lecture number 2 on residues. So in previous lecture we have discussed what is residue and how we can use residues to evaluate certain type of integrals. So as we have discussed in the previous lecture that if f of z has isolated singularity at z equal to z0, then f of z is analytic in the deleted neighborhood of z0 given by 0 less than absolute value of z minus z0 less than r, so that we can represent f of z as a Laurent series in this deleted neighborhood. And suppose this is deleted neighborhood of z0, and suppose we have some simple closed contour around this z0, then integral of f of z along this simple closed contour in counterclockwise direction is given by 2 pi I times residue of function f of z at point z0. So using this formula we can evaluate certain type of integrals. Here requirement is our function f of z has Laurent series expansion in the deleted neighborhood of that isolated singular point z0. So to evaluate this type of integrals, first we will expand f of z in powers of z minus z0, and we will find out residue at z0, which is nothing but coefficient of 1 over z minus z0 in the Laurent series expansion of f of z, and then we multiply that residue with 2 pi I, which will give us the value of this complex integral. So we discuss one more example in this lecture for application of residue to evaluate this integral. So here function f of z is given to be, here f of z is 1 over z into z minus 2 raised to 4. So this function is analytic everywhere except z equal to 0 and z equal to 2. Okay, so we can write f of z is analytic everywhere except 2 points at which denominator is 0. So except z equal to 0 and z equal to 2. Now here we have to evaluate this integral of this function along the positively oriented circle z minus 2 equal to 1. So first we try to sketch this circle and the domains in which functions are analytic, and then we will select particular domain in which Laurent series expansion is valid. Now the function is not analytic at z equal to 0 and z equal to 2. So first we consider appropriate scale, and this is say z equal to 0. Suppose this distance is 1, this distance is 2, and 3 and 4. Now function is not analytic at z equal to 0 and z equal to 2. So now if we consider 2 as center, and if we draw the circle with radius 2, circle with center z equal to 2 and radius 2, then function will be analytic in the deleted neighborhood of this z equal to 2. So we consider circle with center 2 and radius 2. So that will be the circle passing through z equal to 0 and from z equal to 4. So we just try to approximately sketch the circle. So this is the circle with center z equal to 2 and radius 2. Now our contour on which we want to integrate given function is absolute value of z minus 2 equal to 1, that is circle with z equal to 2 as center and radius 1. So that circle is inside this deleted neighborhood. So now we consider circle with center 1 and radius 2. So that will radius 1. So that will pass through this 3 and 1. So this is the contour on which we have to evaluate our function. So this is the simple closed contour which lies in this domain. So we will expand f of z as a Lorentz series in this domain. Our function is analytic outside this domain also, that is we can expand our function as a Lorentz series in this domain also, because function is not analytic at z equal to 0 and z equal to 2 only. So we can expand f of z as a Lorentz series with center 2 in this domain also, but our the domain which contains our simple closed contour is this one. So we will expand f of z as a Lorentz series in this domain 0 to absolute value of z minus 2 less than 2. So with this in mind, first we write down that f of z is analytic in this domain. F of z is analytic in the domain 0 less than absolute value of z minus 2 less than 2, and this domain contains simple closed contour which contains contour C, which is given by circle with center 2 and radius 1. So now we try to expand our function in powers of z minus 2. F of z is 1 over z into z minus 2 raised to 4. So now this z minus 2 raised to 4 we will keep as it is already in powers of z minus 2, and here we have to adjust, we have to minus 2 plus 2. So we rewrite z as z minus 2 plus 2 because we require Lorentz series in powers of z minus 2. So we keep this as it is. Now absolute value of z minus 2 is less than 2, so therefore absolute value of z minus 2 divided by 2 is less than 1. So we can take this 2 common, and this we rewrite as 1 plus z minus 2 divided by 2. So if we multiply with 2 we will obtain 2 plus z minus 2. So because we want to use that standard Maclaurin series of 1 over 1 minus z, we are writing our function in this way. Again we rewrite, we can take these 2 here, and again we consider one more step. This we can rewrite as 1 minus of z minus 2 divided by 2. So now we are able to expand this using the standard Maclaurin series. So as we know, 1 over 1 minus z, the Maclaurin series expansion of 1 over 1 minus z is 1 plus z square in increasing powers of z, and this is valid if absolute value of z is less than 1. So here we have absolute value of z minus 2 by 2 is less than 1, and therefore absolute value of negative of z minus 2 by 2 is also less than 1. So we can use that Maclaurin series expansion by replacing z by this. So here we replace z by minus of z minus 2 by 2. So we have 1 minus z minus 2 divided by 2 plus square of minus of z minus 2 by 2, which will be positive sign, then minus z minus 2 divided by 2 raised to 3 plus z minus 2 divided by 2 raised to 4, and we can write few more terms, z minus 2 divided by 2 raised to 5 plus z minus 2 divided by 2 raised to 6, and one more term we can write z minus 2 by 2 raised to 7, and this is valid because, and one more reason we will write as, because absolute value of z minus 2 is less than 2. This implies absolute value of z minus 2 by 2 is less than 1, and therefore absolute value of negative of z minus 2 by 2 is also less than 1, so that we can use this standard expansion by replacing z by negative of z minus 2 by 2. So now we multiply each term with this z minus 2 raised to 4 and 1 by 2. So first term is 1 over 2 into z minus 2 raised to 4, and here 1 z minus 2 will cancel out, and this 2 into 2 is 4, so we have minus 1 over z minus 2 raised to 3 and into 1 by 4, that is 1 by 4 times z minus 2 raised to 3. Then we consider multiplication of these two. Here we have 2 square, that is 4 into 2, 8, and z minus 2 square will cancel out. So this is plus 1 by 8 z minus 2 square. Then here we have 2 raised to 3, that is 8 into 2, 16, and z minus 2 cube will cancel out. So we have minus 1 over 16 z minus 2, because this z minus 2 cube divided by z minus 2 raised to 4 is equal to 1 over z minus 2, and 2 raised to 3, 8 into 2, 16, and this negative sign. Similarly here we have z minus 2 raised to 4, that will cancel out this, and we are left with here we have 1 over 16 into 2, that is 32. So plus 1 by 32 only. Then negative of here z minus 2 raised to 4 will cancel out, so we have negative of z minus 2 divided by 32 into 2, so that is negative of z minus 2 divided by 64. And the next term is z minus 2 raised to 6, that will so z minus 2 raised to 4 will cancel out, and we have z minus 2 square divided by 2 raised to 6 into 2 raised to 7. So it is going to be z minus 2 square divided by 2 raised to 7. So this we can rewrite as we are getting some pattern. If we observe, here we have 4, so that we can rewrite as 2 square. Here we have 8, that is 2 raised to 3. Then 16, that is 2 raised to 4. Then so power of 2 is increasing, so here we have 2 raised to 5, then 2 raised to 6, 2 raised to 7, and here we will have negative of z minus 2 raised to 3 divided by 2 raised to 8. So negative of z minus 2 raised to 3 divided by 2 raised to 8 and so on. So this is the Lorentz series expansion of given function z minus 2 raised to 4, which is valid in the annular domain 0 less than z minus 2 less than 2. Now we are interested in the residue of this function at z equal to 2. So we have to search for coefficient of 1 over z minus 2. So here we can see coefficient of this term contains 1 over z minus 2 and coefficient is minus 1 by 2 raised to 4. And this is our function which we have denoted by f of z. So we can say that therefore residue of f of z as z equal to 2 is nothing but we can write one more step, the coefficient of 1 over z minus 2, which is nothing but minus 1 over 2 raised to 4, that is minus 1 by 16. So therefore now we have that formula, that integral of f of z over simple closed contour C equal to 2 pi I times residue of f of z at z equal to 2, and it is minus 1 by 16. So 2 pi I times minus 1 by 16, and here 2 will cancel out and value of integral is minus pi I divided by 8. So in this way we can easily find out certain types of integrals using Lorentz series expansion, provided that the contour along which we want to evaluate complex integration must be inside the annular domain in which Lorentz series expansion is valid. So here we had seen two annular domains, 0 less than mod z minus 2 less than 2, and this is also. So we can expand f of z as a Lorentz series in both the domains, but we will select that domain which contains our simple closed contour C. So here this domain contains this circle mod z minus 2 equal to 1. So therefore we have selected this domain and we find out Lorentz series expansion of f of z in this domain. So this is all about today's session. I hope you like this lecture. Thank you very much.